Okay, you stuck me.
So you have 15 minutes, 15 weeks, and you can ask questions, and then for those who register, there is a lunch.
All right, thank you so much for the introduction and for organizing this seminar. And thank you for being present despite the power outages and the cold and I don't know what else. Yeah, so my name is Daniele Michilli, and I work in the field of fast radio burst, which I think I may be the only one here in the institute, so I'm going to give some broad overview, and we're going to learn together what these are and how we can use them. Yeah, one of me is enough. Okay, so first is the first question is what are fast radio bursts and how we can detect them, and then I will move on the on what we believe are the origins of these bursts, and finally how we can use them to study the cosmos. And yeah, as you can see, it's well known that these are mysterious sources that are for a long time have the progenitor have been unknown, and the origin of this burst is still partially a mystery, but I'll show you that we are starting to understand at least some of them. So let's start from the beginning. What is a fast radio burst? As the name suggests, it's a transient signal detected so far only in radio, with maybe one exception. And it's fast because they last for milliseconds. Actually, they range from microsecond up to seconds, but usually about a millisecond. The characteristic that distinguish fast radio bursts from other radio transients is their extreme luminosity and duration. So if you plot the luminosity in the vertical axis and their duration times the emitting frequency in the horizontal axis, you see the fast radio burst occupies an otherwise empty space in this parameter. So they are similar specific luminosity to, for example, AGNs and GRB in radio, but a much, much shorter duration. And similar duration to some galactic transient that you can see in the bottom left of the plot, but with much higher luminosity. And this unique combination of short duration and luminosity make them new probes to study the universe, especially because this luminosity allows us to detect them coming from distant galaxies. And you may think that these bursts so bright are rare, but it's not the case at all. We estimate that in one day, we could detect thousands of them coming from all over the sky, randomly distributed. The problems that radio telescopes typically observe a tiny fraction of the sky, so we don't observe thousands each day, but that's the ultimate goal. And some of them we observe to repeat, about 5% of them. If we look at the same position, we see multiple bursts coming typically a few per hours in some period, and once every few days in other times. But most of them are seen as one-off event. We think that probably between 50% and 100% intrinsically repeat, but on very long time scales that we cannot observe. So observation-wise, most of them are one-off and some are repeaters. The first fast radio burst has been discovered only in 2007, so it's one of these exciting discoveries where we have no idea that this existed before, and the story of how they were discovered is an interesting one, but we don't have enough time, so that's for the next time. In the meantime, I'll tell you that this is what a fast radio burst looks like. I'm not going to go into much detail for now because we are going back to this point in a few slides. For now, I'll just tell you that this is called a waterfall plot. So it's the intensity of the radio signal as a function of frequency and time. And we see the signal that swipes down in frequency. And again, we'll see more about this. Before moving on, I'd like to spend a few slides on how we actually detect fast radio bursts and what are the prospects for the future. Actually, before I move on, there are like questions already about this first part or things that are unclear.
Why did you draw a cat in your slide?
Well, I have a cat here, a dog there. They are helping me looking for fast radio bursts. That's how we do science in my field. So very simply, the way we look for fast radio bursts is quite simple. We basically take a radio telescope, traditionally a big dish. We point it at a certain region of the sky, the field of view of the telescope, and we just monitor the intensity of the signal in that region. And if you see a spike in the signal, you may just have discovered your first fast radio burst, as it happens here. So traditionally, we have these large single dishes. So the first fast radio bursts were discovered by telescopes such as Parkes, GBT, and Arecibo, which are dishes ranging from 60 to 100 meters for GBT and 300 for Arecibo. So these huge dishes. Why do we build big dishes? Just because the bigger the dish, the higher is your sensitivity. However, for fast radio bursts, it's not always better because, as we can see in the left side, if you build a big dish, your field of view is small. You can only observe a tiny fraction of the sky. And so the volume of the universe that you can probe, so the number of galaxies that you can observe, and therefore the number of fast radio bursts that you can discover, is not that high. Alternatively, you can build a smaller dish. You have a larger field of view. You look at large portion of the sky, but with low sensitivity. So again, not many fast radio bursts there. The way we solve this is enabled by computing power. Instead of building a bigger dish, we just have small antennas, and we have many of them. But to connect many of them with an interferometer, you need large computers. And so this has been made possible only in recent years. And for example, this is the Molonglo telescope that has been refurbished. It's like a traditional telescope from, I think, the 50s. And it's been refurbished specifically to look for fast radio bursts a few years back, thanks to the advantage given by computers. Personally, I work on CHIME, which is this radio telescope you can see in this footage. It's a telescope in Penticton, Canada, and it's formed by these 4 cylinders. So they look at the sky in a stripe, south to north, and it's formed by more than 1,000 antennas put on top of these cylinders. And the unique characteristic is that the field of view is much higher than traditional telescopes, but with a good sensitivity. This combination of field of view and sensitivity, together with the capability of being on sky 24/7, looking for fast radio bursts, and a dedicated pipeline with a machine learning algorithm to look for fast radio bursts, has allowed us to increase the number of discoveries by orders of magnitude. You can see in this graph, the number of known fast radio bursts before CHIME turned on and after. However, there is not only the issue of discovering the fast radio burst. we also want to localize them. We want to localize fast radio bursts, to associate fast radio bursts to their host galaxies, so that we can, for example, measure the redshift of the host galaxy, and so the distance of the fast radio burst. But that is not easy. Do you remember I told you that a telescope looks at a patch of the sky and monitors the radio signal in that region, but we don't know, or at least we have a very vague idea of where the source is in this large patch of on the sky. To give you a comparison, this big red circle is a beam of FAST. So FAST is like the largest telescope in the world, 500 meters. And so this is one of the smallest beams we have, but look how many galaxies are there. We have no idea where a fast radio burst comes from in this region. So to know, to associate the fast radio burst with a galaxy, we need an arc-second localization or better. And to do that, we need, again, interferometers. But building an interferometer that has also the characteristic to localize fast radio bursts is technically challenging, and it's something that we have started to do in the recent years, and these telescopes are still under commissioning. So this is where we stand. There are three main examples of radio telescope that can at the same time discover a large number of fast radio bursts and localize all of them to specific galaxies. So the SA 110 ASCAP with its crack update, and especially chime-out triggers, which is what I'm most interested in because I'm part of the collaboration. So chime-out triggers will discover and localize about 2 fast radio bursts per day. And not only this, but the fast radio bursts will be localized to millisecond precision, so an incredible precision that will not only tell us where the fast radio burst comes from, but also where within the galaxy. So not only identify the galaxy, but also the region within the galaxy that the fast radio burst is. So for example, we can study its environment to know the properties of the source. And I find pretty amazing the way it works. It's formed by only 4 telescopes, so CHIME plus 3 smaller antenna, so smaller telescopes across North America called outriggers. And when a fast radio burst is detected, they triangulate its signal to a specific galaxy, calculating the time delay between the different antennas. And to do that, you only need 3. We built an additional 4 for redundancy. And it's very similar to the way that GPS localizes your phone. It's basically 4 satellites calculate the time delay and triangulate your position. Exactly the same principle, except that there are a lot of challenges because we are looking at faint things in the sky and coming from far, far away. And so we had to build, so this technique has been around for decades. It's called VLBI, but has never been done with only 4 telescopes and at these low frequencies together. And so we had to, invent a new technique. And but the good news is that we made it. We are now having the first localizations. We tested it with sources that we already know the position, and it works great. And now we are starting to localize the first fast radio burst with this project. So it's an exciting time in the field because in the next year or 2, there will be a shift thanks to hundreds, thousands of fast radio bursts with a distance and localized to their own galaxies. So let's talk very quickly about the future. The next decade also looks very exciting for the field. we were discussing about the trade-off between sensitivity and field of view. And for the next telescopes, there are experiments that are trying to increase the field of view. So things like burst, we look at the whole sky, all northern sky. However, the way you do that is you just place an antenna on the ground without any reflector. So it sees everything. But then to match the sensitivity of a reflector, you need to add antennas and antennas and antennas. And at a certain point, you hit a limit where you don't have enough computing power. But with the increasing computer performances that we see, these kind of telescopes is starting to get competitive at low frequencies. And so this is the first example. There are another couple already in the design phase. And they still don't match the sensitivity of reflector telescopes, but they are getting pretty close. And they are expected to discover thousands of fast radio bursts too. On the other hand, we are improving the sensitivity by adding more and more antennas with reflectors. So the first example is CHORD, and I'm very interested in this telescope. I'm part of the collaboration, and it's an upgrade to CHIME. You can see CHIME sitting there, right next to the CHORD telescope. And CHORD, this is just a rendering. It's not there yet, but we already put the first antenna on the ground, and it's expected to see the first light in about 1 year. And it's made of more than 500 single dish antennas, small antennas, so that it has a large field of view, but a sensitivity which is higher than the one from CHIME. So it will discover fast radio bursts, more fast radio bursts, about 10 times more, and coming from a larger distance, so we can probe a larger volume of the universe. A similar example is DSA 2000. This is a more traditional array. It's made for imaging, so they are facing some big challenges to look for fast radio bursts, but they are getting there, and I think this is also a very promising instrument with characteristics a bit similar to CHORD. And still down the line, there is, of course, SKA. I guess you've all seen the first image from SKLO a few days ago. And I'm more interested in SKA mid, so higher frequencies, which should start doing science in probably a decade after all the commissioning and finishes. So just to summarize all of this, on your left, I plotted the discovery rate, so what was in 2010, what is now, and what is expected in 5 years. And you can see a dramatic increase. And even more dramatic increase is the number of fast radio bursts that are localized to specific galaxies, which is expected to skyrocket starting this year. Now, I told you what are fast radio bursts, how we detect them, but I haven't told you what actually are fast radio bursts, right? What produces them, how we can use them. So we believe that some of the fast radio bursts come from neutron stars. So these compact remnants from the death of massive stars, with a density just below black holes, which typically have high magnetic fields and rotate fast. We detect many neutron stars in our own galaxies, for example, in the form of pulsars, which emit these pulsating radio signals with characteristics similar to fast radio bursts, so millisecond duration and not all, but some of the properties. They don't have the same luminosity, of course. However, we think that neutron stars can also emit some of the fast radio bursts. The main evidence is that we detected a signal similar to the weakest fast radio burst known, coming from our own galaxy, and it was from a magnetar, so a neutron star with very high magnetic fields. We know that neutron stars can emit millisecond duration signals, as I said, and we also found some fast radio bursts that are similar to the emission of galactic neutron stars and galactic pulsars. For example, I discovered a fast radio burst with a periodicity in its signal, a pulsation like pulsars. With the CHIME team, we found a fast radio burst that must come from an object that is rotating very fast from its polarization profile. And also, thanks to propagation effects, we've put constraints on the size of the object that should emit this particular fast radio burst, and we found that it's a few kilometers. So it must be a neutron star or something similar. Well, I feel like 1,000 kilometers was the upper limit. This solves some of the questions of fast radio bursts, but of course there's a plethora of open questions. For example, how are these fast radio bursts actually powered? How is the magnetic or rotational energy transformed in a radio flare? And where is the emission generated in the star? And what are the physical processes, for example, that generate this signal? And why if you look at the waterfall of a fast radio burst, it's actually different from the one from a pulsar. It has different characteristics. Why is that? Another, I think, more important question is whether neutron stars can explain the whole fast radio burst population. Fast radio bursts come in a big variety. For example, they span almost 10 orders of magnitude in luminosity. Can a neutron star emit all of them? That's hard to model. There are also observational differences. For example, I told you that some are observed to repeat, and the ones that we observe them to repeat, they look like longer in duration and narrower in bandwidth compared to standard fast radio bursts. And finally, if we study their environment, there are fast radio bursts that come from all over the place. There are some we've discovered one in a globular cluster with no star formation, like all the population, no gas, nothing. So it's difficult to imagine a magnetar, a very short-living source. Look at it in there. Maybe there are multiple populations, with gamma ray burst. Years ago, it was the same. We discovered that there were multiple populations. One of the many open questions. But yeah, anything that is unclear until now, because now we're going to move to a different subject. Okay, we can keep the questions to the end, because the origin of fast radio bursts is very interesting. What can produce this energetic and short duration burst? But personally, I'm more interested in how we can use them to study the cosmos. I'd say that at the moment, like 80–90% of the studies are about understanding what fast radio bursts are, especially because we don't have many localizations yet. I hope that there will be a shift in the coming few years. And fast radio bursts can really help us to probe a parameter space that is very difficult to probe at present. And yeah, also this is a clever joke that I hope you will understand in a few slides. So the main way we can utilize fast radio bursts to study the universe is through the effect that plasma have on radio waves. So the radio waves, when they propagate through plasma, they interact with the free electrons and create multiple propagation effects. The main ones I summarize in this slide, and now we're going to see them in not so much detail, but very quickly. So the first and most important one is dispersion. I told you before that a telescope look at a patch of the sky, but that's not completely accurate because it looks at multiple frequencies from the patch of the sky simultaneously. So if we look at the signal, an impulsive signal like a fast radio burst, we'll notice that it arrives first at higher frequencies. And this is because free electrons in the universe slow down the radio waves. And they slow down more lower frequencies. So first, higher frequencies arrive, and then lower, and then lower, and then lower. And this effect, again, called dispersion, goes as the frequency to the -2. So we have this second-order curve. And it's proportional to what is called the dispersion measure, which is the total amount of free electrons between us and the source. Or in other words, the integrated electron column density. Therefore, we can use fast radio bursts to study the plasma that are between us and the source. We can study the amount through dispersion. And now I hope it's a bit more clear, this Lorimer burst, this waterfall I showed you before. Instead of having peaks for each frequency channel, we have a color-coded diagram of the intensity of the signal. And this sweep that you see is due to the dispersion. Then if we mathematically correct for dispersion, align all the frequencies at the same time, and sum them together, we have the pulse profile that you can see in the inset. Here, if we consider a model of the number of free electrons in the Milky Way, we can see that they account only for a small fraction of the dispersion delay. So most of the delay is actually due to electrons beyond the Milky Way, so of extragalactic origin. And this is why fast radio bursts can be used as cosmological probes. Other than dispersion, there are scintillation and scattering. I'm going over very quickly here, and we can discuss it further if you're interested. Scintillation and scattering are caused by turbulences in the plasma. And if you create a waterfall like before, but lasting hours, so a long one, you see that these turbulences in the plasma create over time and over frequencies these scintillas where the signal is magnified and demagnified. And in time, this gives rise to exponential tails in the pulse profiles of fast radio bursts that are more and more extreme at lower frequencies. And scintillation can be used, for example, to estimate the position of the plasma between us and the source, while scattering, for example, can be used to estimate the turbulence in the plasma. Finally, Faraday effect is a rotation of the polarization of radio waves when they interact with a plasma that is magnetized. So we can use the Faraday effect to measure the magnetic fields of the plasma. Oh, what did happen? Yeah. So without going into further detail, we want to use this 3 propagation effects, but there are some challenges. First, I already discussed, we want the source distance, because, for example, let's take dispersion. We know thanks to dispersion, we know the amount of free electrons, but we don't know, if we don't know the distance, we don't know whether the source is closer but the plasma is denser, or the distance is further away and the plasma is more diluted. So if we know the signal, if we know the source distance, we can have information on the plasma. To obtain the source distance, we need to know the redshift of the host galaxy, and therefore we need to a precise localization to pinpoint the host galaxy. The second problem is disentangling the contribution of the different environments. So the fast radio burst, going bottom to up, the fast radio burst travels through its own local environment, which can be sometimes extreme. It crosses the interstellar medium and the circumgalactic medium of the host galaxy, then travels through the intergalactic medium and its clusters and voids and filaments and so on. And finally, it enters the Milky Way and its halo. And from, for example, dispersion alone, we cannot distinguish the different contributions. So, for example, for the Milky Way, we have models, but already for the halo, these models have huge uncertainties. And for the other contributions, especially for the host galaxy, this is basically unknown. With this in mind, I want to speak in the next slides about something a bit more exciting, which is the first results that we are getting with fast radio burst, keeping these challenges in mind and keeping these propagation effects that we can use. Sorry. I think that the first example of use of fast radio burst as cosmological probes was in 2020, when this team used only 8 localized fast radio bursts to confirm that missing baryons are in the intergalactic medium. So missing baryons is this problem in modern cosmology where the number of baryons in the local universe is much lower than was in the past. And it was believed that these missing baryons were in the intergalactic medium. So the authors took 8 fast radio bursts with known distances, and they put it in this graph. The distance, the redshift, is on the horizontal axis, and the dispersion measure of the fast radio burst due to the intergalactic medium is on the vertical axis. And the black line is not a fit. The black line is what you obtain if missing baryons are in the intergalactic medium. And you can see that there is a very good, it goes very well with the position of the fast radio burst. And so, despite only using 8 localized fast radio bursts, I think this is a pretty good initial result in the field, because imagine what we can learn with 10,000 of them. And on the subject, now fast forward 5 years, now another team used 69 localized fast radio bursts this time, the same graph as before, redshift versus extragalactic DM, dispersion, and they could measure the average baryonic density in the intergalactic medium. They also found out that the intergalactic medium is rich in baryons, while circumgalactic medium is baryon deficient, and this brings the authors to say that feedback processes in galaxies must be efficient. And again, this is still in its infancies, but we are already getting some concrete results. this technique can even be used to measure the Hubble constant. Now, I don't think that we'll never reach like 1% through this method, because there are systematics that we cannot solve. For example, the universe is filled with voids and filaments, and they're very difficult to account here. But if we use the same plot as before, like dispersion measure and redshift, here it looks different just because they go at higher redshifts. And we plot fast radio burst on top. Changing the value of the Hubble constant will change the distribution of the fast radio burst in this plot. And so with this knowledge, this team was able to give a pretty good estimate of the Hubble constant, even though, as I said, there are systematics in there. But this was only been done with 16 fast radio bursts. Another couple of quick examples. With only 2 fast radio bursts, these astronomers were able to measure the gas temperature in intra-cluster medium, which is compatible with traditional methods, and I think they compared it with the Senyov-Zeldovich method. But they argue that in the future, with fast radio bursts, we could go to much larger radii than it's currently possible. And with, like, for example, one fast radio burst that was behind a foreground galaxy was used to put constraints on the plasma density and plasma magnetization in the circumgalactic medium. And both of them were found to be pretty low, in contrast with some previous models. We were also, with my team, we were also able to put strong constraint on the amount of free electrons around the Milky Way, so in the Milky Way halo. And it was found that the Milky Way halo is very tenuous. So it's still compatible. What we found is still compatible with most models, but in the lower ends, meaning that it's less dense than what most models usually predict. So these are some examples. There are out there a little bit more, not many more, unfortunately, yet. There are also some other examples that are completely out of my area of expertise, so I'll just summarize a couple of them because I found them very, very cool, but I cannot tell you many details about them. For example, fast radio bursts were used as a completely independent way to put a limit on the photon mass that doesn't have the systematics of other methods. They were used to constrain the Einstein's weak equivalence principle, and this resulted to be 3 orders of magnitude better than previous estimates. And it was estimated, not now, but in the future, when we have more localization, it was estimated that fast radio bursts could even be used to improve results of projects such as Euclid. So I think important for people in this room, about the weak lengthening experiment. In fact, they can be used to break the baryonic feedback degeneracy just by means of counting the amount of baryons in the direction of a large number of fast radio bursts. Perfect. Now, I'm entering in the last part of my talk. You are almost free to go for lunch. So is there anything that is unclear until now before I move on? No, okay. I want now to speak a little bit about gravitational lensing of fast radio bursts, because we've seen many cosmological and astrophysical applications, but I think that one of the most exciting that we haven't explored yet is gravitational lensing of fast radio bursts. The reason we haven't explored it yet is because current telescopes don't detect enough fast radio bursts. So to have one strongly lensed fast radio burst, we need thousands of unlensed ones. And they need to come from far away, because the probability of lensing increases quickly with the distance. But the potential there is large. And I'm mentioning all of this because I actually came to LAM with a project to detect fast radio bursts that are strongly lensed and use them as cosmological and astrophysical probes. So in my last slides, I want to give you a very quick summary of my project. The project is called FLAME, and I probably don't need to explain gravitational lensing to this audience, but just so that we are all in the same page. Here you can see a representation of fast radio burst on the left, plotted with its pulse profile. And it's emitted by some unknown process in a far away galaxy. And a second galaxy in the center of the image warps the space-time, and so it bends some of the radio waves to the direction of Earth. And so the original fast radio burst will now be split in two images of the same fast radio burst that will reach Earth at different times. And also the fast radio bursts propagate through the lens galaxy in the center. And so now all the propagation effects, dispersion, scattering that we mentioned before are visible in its signal, including microlensing from the single bodies in the galaxy, so stars, planets, and so on. They also, each one has its own strong lensing. What we can do with this lens fast radio burst? Well, personally, I'm interested in two goals. The first one is improving time delay cosmography, which is a technique that has been used for decades with AGNs and more recently with supernovae. Basically, you use the delay between multiple images to reconstruct or to measure the Hubble parameter and constrain the geometry of the universe. With fast radio burst, you can do it better because these have very short durations of milliseconds, because you can have more parameters that for the lens, for modeling the lens, which is currently the main limitation in the field. And they don't emit in optical, so you can observe at any magnitude with sensitive optical telescopes. And thanks to their short duration, there are prospects that are currently under study that you may even use them to remove the necessity of modeling the lens, and therefore removing most of the systematics that currently affect this kind of studies. Secondly, I want to use this lens fast radio burst as astrophysical probes to study the lens galaxy and what's inside the lens galaxy. So first of all, for example, thanks again to their short duration, they can constrain like never before the presence of dark matter subhalo, and so inform us about the properties of dark matter, if it's granular, more diffuse, and so on. Thanks to the propagation effect, we can measure to an exquisite precision the amount of plasma and magnetic fields in the lens galaxy. And finally, something that I found really, really cool, thanks to the microlensing, we can even measure the mass, position, and velocity of single objects, so stars and even planets, if there are many free-floating planets, in the host galaxy. And apart from some interesting science that you can do with that, such as measuring the mass to luminosity function, I find it incredible that we can use these sources to measure something as small as a star at a redshift of some. Of course, the big issue is finding this lens fast radio burst. To do this, I developed a method, and I don't have time to go into much detail, but it basically relies on utilizing next generation telescopes, in particular CORD. Thanks to the number of discoveries it will discover, it's expected like 10,000 fast radio bursts per year, and also thanks to its sensitivity, they will come from far away, from a redshift of 2 or more, and so some of them will be lensed, will be strongly lensed, and in the future, I also plan, when available, to use SK-MID. Thanks to its even higher sensitivity, will detect fast radio bursts that are even farther away. And I want to combine efforts with Euclid, and Euclid will provide the optical part to this radio fast radio burst, in particular to get information about the lens galaxy and know the source redshift and model the mass of the lens. With this method, I wrote detailed simulation to estimate the detection rate, and I found out that we should be detecting 5 lens fast radio bursts or more per year, which even with 1 or 2 years is more than enough to reach the goals that I presented you earlier. And yeah, with this, I thank you again for your presence, and I leave you my business card on the screen, so that if you are interested in chatting about this or collaborating, or even going and grab a coffee, feel free to knock at my door. I'm new in the institute, so I'm always happy to meet people. And yeah, thank you. Yeah, I mean, no stupid question, because it will take me like an hour to to go through the details. But basically, it's the microlensing. So I guess you are familiar with the AGN time delay cosmography, but with fast radio burst, we can measure delays down to nanoseconds, and so we can not spatially, but in time, we can distinguish multiple images formed by a single star. So what will happen there is that if you detect a lensed fast radio burst, you will have the first image coming in, and like after a few nanoseconds, second image. And we think we can distinguish an order of probably 5 different images, so 5 different stars, and then the rest will be just blurred together. And yeah, without going too much into detail, but I find this very fascinating, is the fact that the fast radio burst signal is coherent, meaning that you have the phase of the radio wave that, when it's split into 2 images, remains coherent. And so when it comes back again, you can measure the shift in the phase of the radio wave.
About the signal, I missed the part when you explained how the redshift and how the shape of the
I'm not sure I understand the question.
because when the signal comes to us, it gets reshifted, right?
Oh yeah.
So I missed this part because you explained about the density of
Yeah. Yeah, I didn't consider the redshift of the radio signal at all, because usually fast radio bursts are broadband. So even if you shift it, they still look similar. So the redshift doesn't have a big impact on fast radio burst for this reason.
it shifts.
Yeah, exactly. But let's see if I can. Yeah.
The frequency.
Yeah, exactly. But the thing is that if you have a telescope that looks at this portion of it, or a telescope that looks at this portion, it doesn't change much, right? Because they're broadband. So the redshift doesn't have a big impact on the on all the signs that I described.
The frequency is locally shifted, right?
Yeah.
So you're mostly interested in the differential signal, at different frequencies, the delay changes. So it would generate local shift, but if you're interested in differential, it doesn't matter.
Hmm.
That's why. It doesn't change the shape like of the.
The pulse profile of this one.
Doesn't enlarge or shrink.
No, the redshift does not. It's true that usually fast radio bursts are broader at low frequencies, so it's probably you will see. But this is like you will see different parts of the intrinsic emission, right? So yeah, so I don't think it's going to have any particular effect. Also because we are still talking about redshift of 2, so it's not like huge shift.
Maybe I misunderstood this point, but when you shoot some block later on with the dispersion as a function of redshift, there seems to be in relation like this. So
Yeah.
what I mean then the redshift has a
I understand.
okay,
Yeah, no, it's the dispersion, but this is a little bit different point. This is the dispersion that you expect for sources at different redshifts. In another way, if a source is farther away, there are more free electrons between us and the source, and so the dispersion measure will be higher, right? And so that's why you have this linear trend. You just place something farther, you have more electrons, and the DM increases, the dispersion increases.
So I have a couple of questions, but maybe just a very basic practical one. The point about the time and the outriggers.
Mm.
So are you somewhat limited? Naively, don't the outriggers have to be the same size as time itself in order to maintain the level of sensitivity? Similar, maybe not totally different, but then the outriggers have quite a big time, quite a detect.
Yeah, this like was considered in the planning because you can build smaller antennas because now you know where the signal is. You are not searching, so your signal to noise can be lower. how much lower? We calculated that with a second antenna, which is 1/16 of the original one, you can basically localize all of the chime fast radio burst. Because the reason is that with chime, if you don't know, well, with chime you don't know what you're looking for, meaning that you need some high signal to noise, otherwise you have a lot of false positives. And
for the detection, you need chime that much clear.
Yep.
I guess, right, the whole point is localization, so it's surprising to me that, right, I'm sure you've done the careful analysis, it's just a little counterintuitive.
yeah. Now let's say with math, right? Chime now detects something that has a signal to noise of 10. Now I know where the signal is. Without trigger for the localization, I can go down to a signal to noise of 5. And for the localization, the total signal to noise is the geometrical average between the two signal to noises. And so I have a factor of 16.
Regarding the FRB itself, do you have some correlations between the characteristics of the FRB and the characteristics of the host galaxy?
Yeah. Yeah, very good question. We looked for it, but we didn't notice any. We found, for example, an easy one is checking repeaters versus no repeaters if they come from different environments. Both of them come from a lot of different environments. We found fast radio bursts in dwarf galaxies that were repeaters or not. We found them in big spirals. We didn't find many in elliptical. I think we found 1 or 2 in elliptical galaxies. So, yeah.
I have a question. So at some point you mentioned the false detection. So what is the origin of false detection and how they many?
Oh, in radio, I mean, radio is flooded with interference. Like, everybody uses cell phones, and so many of the false detections are just human-made interference that come into the signal. We have a machine learning pipeline that distinguishes the two, but of course it's not 100% perfect. For our pipeline and for chime at these frequencies, the main source of interference is radio waves emitted by far away that are reflected by transit airplanes. So so they are far away, they move on the sky, and they have like all shapes. So we figured this out because we compared burst of false detections with local airport times, and they matched very well. Let's see. In the cosmological application, the intergalactic medium basically doesn't come into play because you measure the delay between the two images. There's not much there you can do with the intergalactic medium because the two images will be separated by an arc second. And so they basically travel quite close together, or at least at distances that are smaller than typical changes, typical scales in the intergalactic medium.
I meant circumgalactic medium.
Exactly. The thing that you can do is that since they are close you can remove all the contribution of the intergalactic medium, of the Milky Way, of the host galaxy, and you are only left with the contribution of the lens galaxy, because that's the only part where they are like actually separated by kiloparsec, and it matters. And so you can study, that's why you can study the plasma and magnetic fields in the lens galaxy in amazing detail, because you remove all the other contributions, and that's what's the only thing left.
Right, so it depends on the organization of the lenses as to the radial sampling and what scale you can probe. That was my question, right? So it's what? Is it more interstellar medium, circumgalactic medium, close circumgalactic medium?
Exactly.
I just don't know until you have your sample.
Well, intuitively, I'd say mostly interstellar medium, because that's the largest contribution and also the largest variation in time. And keep in mind that these will all be giant elliptical galaxies.